Welcome to Operation Research. In this video, we will learn about how to solve a linear programming problem, that is LPP, with the help of Simplex method, which have three decision variables. The problem statement is given to us. We have been given an objective function and we have been given a three different constraints which are of less than or equal to type. And the problem is to maximize the value of objective function. Now, before we start actually solving this problem, let us try to understand the complete procedure how to solve this problem. These are the steps involved in solving a LPP by Simplex method. First step is to convert the LPP to a standard form. Second, form an initial table of LPP. Third step is to establish an initial feasible solution. Fourth step, locate the scope for improvement. Fifth step, identify the entering and departing variable. Iterate it until we get an optimum solution. So let us see how these steps are executed. So here is a flow for solving the LPP by Simplex method. So the first step is to convert LPP into standard form, create an initial table, establish an initial feasible solution, and then we look for the scope for the improvement. And that is computed by Cj minus Zj value. So now we will see what exactly this Cj minus Zj value while we solve the example. If the Cj minus Zj value is positive, means it is greater than 0, then we can identify the entering variable and departing variable and update the table. The meaning of Cj minus Zj is positive means that there is a scope for improvement the current solution. Now note that this particular situation is valid for the maximization type of an problem. If the Cj minus Zj value is less than 0, that is it is negative, then we can say that we have reached to the optimum solution, and at that point we can stop, and that is the optimum value of our problem. So let us begin with our problem. Now the first step is to convert the objective function and constraint into a Simplex standard form. We have three decision variables, that is x1, x2 and x3. You can note that we have a maximization type of problem and all the constraints are of less than or equal to type. So we will need three slack variables. Let us call them as s1, s2 and s3. Let us convert the constraint in a standard form. So our first constraint will become 4x1 plus x2 plus x3. Now we will add slack variable s1 over here, which is having a coefficient of 1, and we also need to add other two slack variables with 0 coefficient. So this will become 0s2 plus 0s3, which is equal to 30. Now for this second constraint, we will write down as 2x1 plus 3x2 plus x3 plus, now we need to include this s1 over here but with 0 coefficient. S2 will be the slack variable for the second constraint, and also this S3 will have a 0 coefficient, and right hand side is 60. Third constraint will be like this: x1 plus 2x2 plus 3x3. Now here the coefficient of S1 and coefficient of S2 will become 0, and S3 will be the slack variable for the third constraint, and right hand side is 40. Also we need to add all these slack variables in the objective function. So z will become, now my objective function will become now 3x1 plus 2x2 plus x3 plus 0s1 plus 0s2 plus 0s3. We have added this 0 coefficient for the slack variables in this objective function because they do not contribute anything in the profit, that is the value of z. Now with this, now let us create the initial simplex table. This is the simplex standard table that we are going to fill with the information that we have derived in the last step. Now this particular row represents the objective function. So in objective function we have 6 variables. So we have added 6 columns, 1, 2, 3, 4, 5 and 6 to this table. Also we have 3 constraints. So we have added 3 rows here. The Cj value represents the coefficient of variable which are present in the objective function, and this particular Cj value represents the coefficient of variables which are there in the basic variables. Basic variables are the variables that are present currently in the solution. Right hand side or RSH represents the right hand side of these equations. Replacement ratio that we are going to evaluate and which will be the deciding point for the departing variable. Zj represents the profit and Cj minus Zj represents the opportunity that we are going to evaluate. Now let us start filling this table. So consider this objective function. We have 6 variables over here. So this your x1 is decision variable, x2 is decision variable, x3 is also decision variable, and s1, s2 and s3 are your slack variables. Coefficient of this x1 in the objective function is 3, so we will be writing 3 over here, 2 for x2, 1 for x3, 0 for s1, 0 for s2 and 0 for s3. Now at this initial point we assume that there is no production and all the resources are idle. So this s1, s2, s3 represent the slack variables, and we are going to put these 3 variables at the solution. So I will be writing s1 over here, s2 over here and s3 over here. This point is called as a point of no production, meaning is that we consider the values of x1, x2 and x3 to be 0, and all the values of this particular resources that are present in the constraint will be assigned to this s1, s2 and s3. Also we have to write down the value of Cj for these 3 variables, and it will be 0, 0 and 0 for all s1, s2 and s3. Now consider the first constraint and write down the coefficient. So for this first constraint, the coefficient of x1 will be 4, coefficient of x2 will be 1, x3 will be 1, s1 will be 1 and s2 and s3 will be 0, and the right hand side is given by this 30. So I have represented this first constraint completely for this first row. Now going for the second constraint, so it will be 2, 3, 1, 0, 1, 0 and 60. So this is the second constraint that we have just added, and looking for the third constraint, so it will be 1, 2, 3, 0, 0, 1 and right hand side is 40. Now you can note that value of x1, x2 and x3 are 0 at this point, and values of s1, s2 and s3 are 30, 60 and 40. Meaning is that all the resources are idle. Now once we are ready with this simplex initial table, the next step is to calculate the value of Zj and to calculate the value of Cj minus Zj. To calculate the value of Zj, we need to multiply the 0 into 4 plus 0 into 2 plus 0 into 1, and it will give me the value of 0. Similarly, for this x2 column, it will be 0 into 1 plus 0 into 3 plus 0 into 2, and ultimately it will become 0. Now all these values will be definitely 0 because the coefficient of this s1, s2 and s3 are 0. So we can directly write 0 values for all these things because this is an no production point and there will not be a profit right now. We need to calculate the value of this Cj minus Zj. Now the Cj value is given by this and 0 is given by this. So 3 minus 0 will be 3. Similarly, this 2 minus this 0 will be 2, and this 1 minus 0 will be 1, and 0 minus 0, 0 minus 0 and 0 minus 0 will be 0, and ultimately this Zj value will be 0 because it is a no production point. Now if we look back and see what steps we have completed, so we have converted the LPP in a standard form, we have created the initial table, and we have established the initial feasible solution, and also we have computed this value of Cj minus Zj. Now this Cj minus Zj value indicate the scope for the improvement. Now we are at this stage. Now we have to look for whether we are getting any positive Cj minus Zj value. If we get any positive value, then we need to identify the entering and departing variable and we need to update the table. Once we reach to the point where we get the Cj minus Zj value as either 0 or negative, at that point we can stop. So let us move to our example. Now here you can note that the values of Cj minus Zj, we are getting either positive values or 0 values. So positive value indicates that there is a scope for improvement in the current solution. And now we will select the maximum positive value, and that is corresponding to this column x1. So meaning is that this x1 will become now my entering variable, right? And I have to calculate the leaving variable or departing variable, and that must be from s1, s2 and s3. To evaluate this departing variable, we need to compute the value of this replacement ratio. Now this column, which is having the highest value of Cj minus Zj, I have indicated it as an entering variable. So x1 is my entering variable, and I have indicated this particular column as key column. And now we have to evaluate the value of this replacement ratio. Now replacement ratio is given by this solution RSH, that is 30 divided by the corresponding element in the key column. So I can write it like this: 30 divided by 4 will give me the value of replacement ratio, and that will be 15 by 2. And for this thing it will be 60 divided by this 2, so it will be a 30 replacement ratio, and here it will be 40 divided by this 1, and that will give me the value of 40. Now we have to consider the minimum positive value of this replacement ratio as the departing variable, and here we can note that this become my departing variable, and this corresponding row will become a key row, and this intersecting element of key column and key row will become my key element. Now I need these three elements for revising or updating this table. So now let us update this table. Now we need to take a blank table as shown in here, and we need this previous table for the reference to fill this table. Okay, now what is the important change in this table is that here x1, x2, x3, s1, s2, s3 variables are not going to change, but for this basic variable thing, now the x1 will take the place of this s1. So this x1 is going to replace this s1. So I have written s2 and s3, which are not going to change, but at this position Instead of x1, I will be writing the x1 and its coefficient in the objective function is 3 that we have written. Now the first step to update this table is to get this corresponding key row. So this x1 that we have just added in this current solution and the corresponding row we called it as an key row. So this will become my reduced row and the elements for this particular row are given by this formula. So new element in this reduced row is given by corresponding element in key row. So corresponding element in the key row from the previous table divided by this key element. So this 4 is our key element. So if I try to evaluate the element at this point, so it will become 4 divided by 4 itself, because same is the key element, so it is given by 1. For this particular position it will be 1, so previous element is 1 divided by key element is 4, so this will become 1 by 4. It will also become 1 by 4, 1 by 4, and this will remain as 0. This will also remain as 0, and this solution RSH will be given by 30 divided by 4, so I can write it as 15 divided by 2. So I will recommend that do not put these values in some decimal points, because that will not be much helpful for the further calculation. Now let us go for evaluating the values for these two replaced rows. Now we need to derive the elements in these two rows and we call them as a replaced row. So the new element in the replaced row is given by this formula. Now let us evaluate the new element for this replaced row for this particular place, and it is given by this formula. So I will be writing here as element in the old row. So element in the old row is 2. So this is the element in the old row minus bracket intersecting element in the old row. So again intersecting element in the old row is 2 only into corresponding element in the reduced key row. So we have to consider this element because this is the corresponding element in reduced key row that we have derived just now. So that element is 1. So this will give me a value of 0. So here I will be putting value as 0. Let us try to derive the same thing for this position. It will be given by element in the old row. So element in the old row is 3 minus intersecting element is 2 into 1 by 4. So this is given by 3 minus 1 by 2, that is 5 by 2. So I will be writing value as 5 by 2. In similar way, we can derive the values for the remaining elements. Now same thing can be applied for this S3 row. So the formula is same. So element in the old row. So element in the old row is 1. So I am referring this element minus intersecting element is also the same, that is 1 into corresponding element in the reduced row. So it is given by this 1. So it will become 1 minus 1 is value give me a 0. So I can write value of 0 over here. Now let us evaluate the other values in a similar fashion. Now once we are ready with this table, let us evaluate the value of z, and which is given by this 3 into 1 plus 0 into 0 plus 0 into 0, and that will give me the value of 3. So similarly I will evaluate the values for the remaining things. Now once we are ready with these values of zj, the next step is to calculate the value of this cj minus zj. So this is given by 3 minus this 3 will be coming as 0, and 2 minus this 3 by 4, that is 2 minus 3 by 4 will give me the value of 5 by 4. Similarly, I will calculate the remaining value. Now here you can note that we have got some positive values over here. So the maximum positive value is given by this 5 by 4. So this is 5 by 4 and this becomes my key column, or this x2 becomes my entering variable. Now this becomes my key column, right? And now I have to evaluate the value of this replacement ratio. So replacement ratio value is given by this 15 divided by 2 divided by 1 by 4. So that value is given by 15 divided by 2 divided by 1 by 4. So that gives me a value of 30. So I am writing 30 over here, and accordingly I will calculate the values for the remaining positions. Now here you can note that the minimum value of this replacement ratio is 18, and we are interested in minimum positive value, and this particular element or this particular variable S2 will be my departing variable. And now this particular row with S2 variable becomes my key row, and this 5 by 2 becomes my key element. Now here we are going to replace this x2 by, or we are going to replace this S2 by this x2. So x2 will come over here. Let us prepare one more fresh table. Let us call this iteration now as iteration number 2. All the values will remain the same, that is x1, x2, x3, s1, s2 and s3. Only change will be this s2 will be replaced by this x2. Now it is time to fill this table, fill this updated table with the help of the table that we have derived previously and by using the formulas. We call it as an iteration number 2. Now the corresponding row, that is corresponding to this key row, will be your reduced row, and that is given by this formula. So let us evaluate this element. So it is given by corresponding element in the key row. So the corresponding element in the key row is 0 divided by the key element is 5 by 2. So the value is given as 0. Similarly, for this position, the corresponding element in key row is 5 by 2 divided by key element, the same is the key element, so its value will be 1. So similarly, I will evaluate values for the remaining positions. Now evaluate the values for this replaced row, and the formula is given by this thing. So new element of a replaced row, so new element in the replaced row is given by, so I am writing over here, element in the old row. So element in the old row is 1 minus intersecting element of the old row. So intersecting element of the old row is given by this 1 divided by 4 into corresponding element in reduced row. So corresponding element in this new row is 0. So this will become 1. Okay. Similarly, I will evaluate values for the remaining elements. Same thing applies for this third row, and let us evaluate element at this position. So if I apply formula at this position, element in the old row is 0 minus element in the intersecting element in the old row, that is 7 by 4, into corresponding element in the reduced key row. So it is again a 0, so the value will be 0. So I can write 0 over here, and now I will evaluate the values for the remaining elements. So here I got the values for the remaining elements. Now here you can note that the value of x1 is 3 over here, value of x2 is 18 over here, and value of s3 is 1 over here for this iteration number 2. Now it is time to evaluate the value of this z. So it is given by 3 into 1 plus 2 into 0 plus 0. So the value will be 3. Similarly, we can evaluate the values for the remaining elements. So you will get values something like this. And now evaluate the value of Cj minus Zj. So it is given by 3 minus 3 is 0, 2 minus 2, 0, 1 minus 1, 0, 0 minus half is minus half, minus 1 by 2 and 0. And here you can note that the value of z at this point is 45. Now at this point you can note that we are not getting any positive value for the Cj minus Zj. All the values are either 0 or negative. So we can say that this is the optimum solution we have reached in iteration number 2, and the corresponding values for x1 are 3, 18 and S3 is 1. So it is the unused resources, S3 is the unused resources, and value of Z is given by this 45. Also you can note that the value of x3, which is also our one of the decision variable, is also have a value of 0. So this is the optimum solution that we have reached. Thank you.